Hey guys, BuildZoid here, and today we're going to be taking a look at the PCB of the MSI MAG X870 Tomahawk Wi-Fi motherboard. Now this board was provided by MSI at my request, so a big thank you to them for sending over a review sample. And before we get into this, a quick disclaimer. This is not a review, and I'm not an engineer. And yeah, you should just kind of be aware of that. Also, if you like the content I create, there are links down in the description that you could check out, and that would be much appreciated. And with that out of the way, let's get into it. So, it should be pretty obvious why I requested a review sample of this motherboard. And that reason is that this is one of the cheapest X870 motherboards to come with a postcode. Now, admittedly, postcodes on AM5 aren't as detailed as on some Intel boards, but I still prefer having a postcode compared to just having the color-coded troubleshooting LEDs. So yeah, this is like, especially if you're doing a lot of memory overclocking, like having the postcode is just nice. And from a like overclocking perspective, there's not really much else to worry. Like obviously there's like the memory topology to worry about with the boards, but unfortunately, until you have a board, you just don't know how good that is. So yeah, whereas this is like an easy, like this is a feature that you can just kind of see and it's like, oh, I want that. So, yeah. So basically the prior, like the sort so basically the thought process for me is like, ooh, this is one of the cheapest options with a postcode. I wonder if the rest of it's good. So that's the thought process behind requesting the review sample. And yeah, thank you to MSI for actually sending one over. There are also color-coded troubleshooting LEDs, which are kind of redundant when you have a postcode because they just don't give you as much detail, but it doesn't hurt to have them. Now, one neat thing that I noticed when I got the board is that we have a fail-safe jumper over here, and it doesn't work. As in, I've managed to get this to trigger, but it didn't do what I was hoping it would do. So I had some incredibly unstable memory settings, and I wanted to get in the BIOS without having to clear the CMOS. And yeah, this turned on, and I got the message. You're like, the board was like, oh, you're in safe mode, and my incredibly unstable memory overclock was still active. So, in typical AM5 motherboard fashion, the safe boot function doesn't work. Um, so that's not really that surprising, but it is a bit disappointing because if this did work, that would have been really, really cool. But as it is, it's the same as any other AM5 motherboard. It just doesn't do anything. Or at least it doesn't do the thing you'd be hoping it does. Because the one thing it did actually do is like drop the PCIe speed down to Gen 3, but like that wasn't what I was hoping for. I wanted the memory overclock turned off. So yeah, it didn't do that. Anyway, above that we do have a clear CMOS jumper, and there's also a clear CMOS button in the rear I/O. So, you know, if you have access to the back of the case, the jumper isn't really that relevant. But if your system is in some kind of setup where you can't reach the rear I/O conveniently, you could always just wire the clear CMOS jumper to your like reset button or something on the front of the case, and have an easily accessible clear CMOS button that way. And that is something that, like with AM5, is kind of a necessity. Also, one thing I appreciate about this board is that the clear CMOS jumper and the clear CMOS button don't require you to turn off the power supply. Yeah, because that is an issue with some other AM5 motherboards that I can't believe because like there's DDR3 boards that don't require you to turn off the power supply in order to clear CMOS. So I appreciate the fact that like MSI has implemented clear CMOS the way it should be implemented. I can't believe I'm pointing that out, but here we are. I have a certain other X870 motherboard where if you jump the clear CMOS and the power supply is turned on, nothing happens. And that one also has a button, and if you press the button and you don't turn off the power supply, nothing happens, which is just I don't understand because like from a design perspective, it's basically a matter of having a single extra MOSFET. So, um, yeah. Good job, MSI, on having a properly implemented clear CMOS jumper. I can't believe I'm saying that. Anyway, other noteworthy connectors internally, you do get a USB Type-C port over here. Well, internal USB Type-C with 27 watts of like power delivery. And there's a bunch of M.2 slots. So you've got these two over here from the chipset. This one shares PCIe lanes with this PCIe slot. The board does give you the option to disable this M.2 slot and send all of the PCIe lanes to the PCIe slot over here in the BIOS. Anyway, the motherboard manual has more details on the lane allocation. In case I made a mistake, because to be completely honest, I don't actually care that much about M.2 slots. Then we have this M.2 slot over here, which is wired to the CPU, and this one's doing something kind of neat, because with X870, one of the requirements is that you get this high-speed USB controller over here, and the thing is, this needs a lot of PCIe bandwidth, so the way this is wired is that normally this runs X2 Gen 5, and the other X2 Gen 5 goes to the USB controller. But on this board, you have the option to go into the BIOS and disable this thing, and then this this M.2 slot will run Gen 5 by 4. So that's pretty cool, because that is not a thing that you get on many other motherboards. So props to MSI on doing that, because yeah, if you don't care about the high-speed USB ports, then you can just have more M.2. Also, it's worth noting, if this is running Gen 5 by 2, it also, if you stick a Gen 4 drive into it, it's just going to be Gen 4 by 2. Because PCIe, the by 2, by 4 for PCIe, those are physical connections. Those aren't logical stuff, those are physical wire connections. The wires don't magically multiply themselves if you downgrade the speed. Right? So, that's just something to keep in mind. So yeah, neat feature that you can change the PCIe allocation on that M.2 slot. And then this one is just wired directly to the CPU, full X4 bandwidth, Gen 5 all the time. So nothing wacky going on with the PCIe lanes for that one. And then of course this PCIe slot over here is X16 Gen 5 all of the time. So yeah, no lane splitting on this slot either. At least not as far as I know. And then you do get this quick release mechanism. And this one's actually, I really like this one, because basically you push the button and it locks the card, and then you push the button again and it unlocks the card. So it's not you don't have to press and hold while pulling the GPU out. You just, it's a toggle latch, which I really like. Because that's just way more convenient, because you can just unlatch it and then pull the card out with both hands, instead of awkwardly, using one hand to press the button and the other hand to pull the card out. So I think this is really cool. This is probably my favorite quick release mechanism that I've seen, other than the one that Gigabyte has, where they just extend the PCIe clip thing. They'll just give you an extra lever on the latch here. So because that makes it easy to reach with one of your fingers while grabbing the card. Unfortunately, that's not usually an option for the top PCIe slot, because the M.2 heatsink gets in the way of that. So yeah, anyway, so that's our internal connectors. Oh, and there's also 4 SATA ports and USB ports, and you can just check the motherboard manual for that kind of stuff, right? Anyway, rear I/O, clear CMOS button, big fan of that, especially because it actually works even if you don't turn off the power supply. And then below that, we have a BIOS flash button, so you can update the BIOS of this motherboard without even having a CPU installed. This also means if you buy an incompatible CPU, you can just update the BIOS to the correct version. This can also sometimes recover from corrupted BIOSes, and you can also force BIOS downgrades, because sometimes you'll get a BIOS update that prevents you from downgrading the BIOS using the usual update utility. Whereas with this button, you can typically force BIOS downgrades whenever you feel like it. That's a neat little feature to have. Then we have the 40 gigabit per second USB ports. One thing I find kind of funny about the high-speed USB chip is this thing has its own heatsink. That's what these screw holes are for. This thing has a rather substantial heatsink. I think it has a bigger heatsink than the 10 gigabit LAN chips usually do, which I guess makes sense, because this thing is technically faster, and it has power delivery to yeah, it has power delivery support. So I guess that makes sense, but I just find it kind of funny that a USB chip has a rather substantial heatsink attached to it, because it's not really something you think about oh, USB controllers needing cooling. Anyway, then we have a bunch of Type A USB ports, which I'm a big fan of because, funnily, literally the only device I own that actually has a USB Type C port is my phone. So yeah. And then there's 5 gig LAN from Realtek, another USB Type C port. This one doesn't have any wacky lane sharing going on with it, as far as I know. Wi-Fi 7 and optical out, and then line mic in and line out for the audio. So cut down audio section, which is pretty typical for like motherboards these days. Because if you really care about audio quality, you should probably get an external solution. Anyway, so that's the rear I/O. Let's move on to the power delivery. We get 2 8-pin power connectors. You only need to plug in one of these because, yeah, Ryzen CPUs don't pull that much power. Like, there's really no reason for that second 8-pin to be here as far as I'm concerned, especially since MSI is using the high current variant of these power connectors. So we've got solid metal pins. There's a folded metal version that's like lower current handling capacity because the pins just are thinner. Yeah, and since we're on the topic of solid pins, the 24 pin is all solid pins, which just makes it more annoying to unplug and plug in. I mean, some of that's also just down to the like tolerances on the plastic housing itself, but that is one thing I noticed with the low current connectors, especially on the 24 pin, they tend to be easier to plug in. And there's also an 8-pin power, like 8-pin 8-pin PCIe connector down here, which I don't understand why it exists. MSI advertises this as like extra PCIe slot power, but it's like, this only has 3 PCIe slots. This is a 1X. I actually just don't understand what this is for. It might be more about like USB power delivery or something than it is about the PCIe slots, because the highest PCIe slot power draw cards are things like the RX 480. Like a 4090 doesn't pull a lot of PCIe slot power. And even if you use an RX 480, you'd need to use 3 of them before this becomes necessary. And another thing I don't get about this is like if you have if you have cards that pull a lot of PCIe slot power, well, you're going to need more than one of them in order to overload the 24 pin. And if you have more than one of them, they pull a lot of power, they probably have pretty substantial heat sinks. So like, how are you going to plug this in? Right? Because like there's going to be like a heatsink right here. So I don't understand what this is supposed to do. It makes 0 sense to me. It kind of reminds me, like, this used to be a standard feature on like there was like there was a period of time when you would get this on like a bunch of motherboards that didn't need this. This feels like it's a return of that, where it's like, yeah, there's this just random extra power connector on your motherboard that serves no real purpose. Because yeah, like I actually don't understand what this is supposed to solve. Like, you're just not going to have any PCIe cards that pull enough power to justify plugging this in, unless they also block you, like prevent you from physically plugging this in. So yeah, dude, I just like, it's just there. It doesn't really hurt anything by existing. Yeah, I don't get why it exists. Anyway, let's talk about things that I do understand why they exist, which is CPU power delivery. Because, yeah, without that, your CPU wouldn't work. We've got a whole bunch of power rails, as is normal for AM5. So we have VDD MISC down here. This is basically, this is primarily power supply for the Infinity Fabric links. As well as like other stuff, which is why it's MISC for miscellaneous. There's like other things that run off of that AM like it's too much random stuff that's powered off of this rail, so it doesn't have like a specific name because it powers random things. I unfortunately there's no. I unfortunately don't know exactly what it powers, but from an overclocking perspective, primarily the Infinity Fabric links. As in, like, this is the voltage that gets used for generating VDDG IOD, VDDG CCD. And GIMP is being stupid, because of course it is. Love this application. Oh, and it's still doing it. Okay, you need to stop. Okay, now it's fine. Anyway, then up over here, we have VSOC. Yeah, we're going to go up here. So SOC power. Then this right here is VDDIO. So that's memory controller juice. And then the rest of this is vCore. And in terms of the controller setup, well, let's just start with the most important power rails, that being vCore and VSOC. The controller is this chip right over here, which is a Monolithic Power Systems MP2857, running in 7 plus 2 phase mode. So we've got 7 for vCore, 2 for SOC. Now on vCore, we've got 2 power stages in each phase. Right, so like this is 1 phase over here. So in total, there are 14 power stages. And the power stages being used are Monolithic Power Systems MP7670s. These are 80 amp smart power stages. Also, this is like a nominal current rating. It's not like you wouldn't actually want to put 80 amps through these, because at that point the efficiency is atrocious and they're going to be uncoolable, especially when you have 14 of them. But anyway, so yeah. And actually, this is one thing that bugs me with especially modern high-end motherboards, is that the nominal current ratings for power stages have gotten completely out of control. It used to be that like 40 amp power stages were not great, then 50 amp power stages were better, and then like 60 amp power stages were really good, and then eventually we started seeing like 70 amp smart power stages, and those were just amazing. And then you go from the 70 amp smart power stages to like 100 amp, like now we have like smart power stages with nominal current ratings of like 90 amps, 100 amps, 110 amps. And the funny thing about all of these like super high nominal current rating smart power stages is a lot of them perform really similarly in terms of actual thermals, because the peak current rating is just not relevant at all. And it annoys me, because I feel like this is probably just like a marketing push from the motherboard vendors to get higher nominal current ratings instead of any actual meaningful improvement in the smart power stages. Because I've tested boards where like 70 amp smart power stages seem to run more efficient than like 110 amp nominal power stages. And another issue is that like each manufacturer has their own way of speccing this nominal current rating. So like 70 amp parts from one manufacturer are not equivalent to 70 amp parts from another manufacturer. And like that's the funny thing, is just that's probably why like I tested a board where like 70 amp parts with no VRM heatsink were getting better thermals than 110 amp parts with no VRM heatsink, which in theory should be a relatively equivalent test unless there's a major difference in the heat dissipation capabilities of the PCB itself. But both of the boards, actually the hotter running board was on a 10-layer PCB. So like, unfortunately, this number right here is not very useful. So yeah, I just want to point that out. Not that it's a problem. Like basically the way I like to think about it is if the nominal current rating is higher than 70 amps, it's good enough. Like, because everything above 70 amps is like, there are some parts that are better, but a lot of them are kind of the same. So like 80 amps, 90 amps, 100 amps, like without actually testing them in like a very controlled environment, because obviously if the motherboard has different VRM heatsinks, then like less efficient parts with more heatsink are going to run cooler. More efficient parts with worse heatsinks are potentially going to run hotter. So that doesn't really tell you, you know, how good the actual underlying power stages are. It tells you how the like overall like the combined combination of all of the parts of the PCB, the heatsink, the inductors, how all of those combined perform, which doesn't necessarily require that, you know, the 110 amp parts actually are more efficient. I mean, these are 80s. But the reason I point that out is because I see absolutely no reason to have power stages rated for more than 80 amps. Like, it just doesn't make sense to me. So that's like a good thing for this motherboard. But yeah, like the main reason I'm pointing this out is for like comparisons to later boards, because yeah, there's boards out there with 110 amp power stages. Not that it actually means anything. And I feel like you should be aware of that because I do think, like, as far as I can tell, the only reason these insanely high nominal current rating power stages exist is marketing. And I hate marketing. So, there. Anyway, these are smart power stages, so they integrate a whole bunch of monitoring and safety features. I mean, the main thing is the monitoring. The defining feature of smart power stages is that they have a dedicated current monitoring pin that just connects to the controller, which makes VRM design somewhat simpler. And also that current monitoring functionality built into smart power stages is generally more accurate than the current monitoring that you get with like DRMOS component, with normal like DRMOS components. But these monolithic power systems ones also integrate over temperature protection, over current protection, and a whole bunch of other protections that we're not going to get into because they're annoying to explain how exactly they work. So, yeah. I wish I could say these are top of the line power stages, but at least on paper there's like 110 amp parts out there, so you know, for what little that means. But anyway, we do have 14 of these. In the vCore VRM, right? Because we do have 2 of them in each phase. And the way this is set up is there's no doublers. It's just one PWM signal going into 2 power stages at the same time. So they turn on and off in phase with each other, right? Because they literally run off of the same PWM signal. Now, funnily enough, this VRM is basically big enough to power a 4090. Which should tell you just how completely unnecessarily excessive it is for powering a 9950X. Because, yeah, 9950Xs pull a lot less power than 4090s do. Anyway, let's talk theoretical heat outputs. So, assuming a switching frequency of 500 kilohertz and an output voltage of 1 volt, which is a bit low, but unfortunately the documentation for these power stages is spec'd at 1.8 volts and 1 volt. And 1 volt is like NVIDIA GPUs, which makes sense because monolithic power systems is very popular for NVIDIA GPUs, NVIDIA GPU power delivery. So it makes sense that they'd have a voltage spec that makes sense for NVIDIA GPU designs. And then 1.8 volts is for Intel server CPUs, which doesn't make sense because no, that makes sense, but like. Yeah, annoyingly enough, neither of those is really relevant to Ryzen CPUs. For Ryzen CPUs, you'd ideally want something like 1.2 output voltage. So 1 volt is close enough, but not ideal. So just keep that in mind. Anyway, so 500 kilohertz, 1 volt, 200 amps output. This VRM should only produce about 13 watts of heat from the power stages. So that's not accounting for losses in the inductors or the power plane. On a lot of motherboards, the power plane actually is a very substantial source of power loss. Because, yeah, you're going to be squeezing a whole lot of current into the CPU socket, right? And now this does use an 8-layer PCB, so it really, like, 8-layer PCBs for 200 amps really isn't a problem, but, like, 6-layer boards can have issues. Not that that's a concern with AM5, that's more of an Intel concern on, like, Z790 or something. Anyway, now if this was like, this is just a guess on my part, if we went from like 1.1 volt output to about 1.2 volts, this would probably be like 15 watts of heat, maybe 14, something like that. There's like not, like there is an increase in heat output, but it's not as big as the increase in output voltage. So one sort of funny thing about efficiency ratings with power stages, the efficiency generally gets better as you output more voltage. So at like 1.8 volts, the efficiency is a lot better than at 1 volt. And at 1.2 volts, it'll be slightly more efficient than at 1 volt. So actually, this is probably a bit high. It'd probably be like 14, 15, somewhere between 14 and 15 watts for 1.2 volts output voltage. Anyway, 200 amps is already more current than a 9950X pulls on stock settings, because the stock current limit for a 9950X is 170 amps. Basically what this means is this VRM is capable of powering a 9950X, or, I mean, I haven't tested this, but on paper, this should be capable of powering a stock 9950X with no VRM heatsinks. And considering that this also has an 8-layer PCB and relatively low inductance inductors, we'll get to that, Yeah, I really can't imagine this struggling to power a 9950X, even if the board didn't have VRM heatsinks. So yeah, massive overkill. 300 amps output current, about 20 watts of heat. At this point, the VRM heatsink does become necessary, but I don't think you're hitting 300 amps unless you run your CPU on liquid nitrogen. So that's not really a concern. 400 amps is... I am not sure you can actually get a 9950X to pull 400 amps, but maybe. And if you somehow did that, the VRM would produce about 29 watts of heat. This is also, like 4090 territory. Like I mentioned earlier, this is basically a 4090 VRM strapped to a motherboard. For a CPU. Now, well, the big difference between a like CPU power delivery and GPU power delivery is if this VRM was on a 4090, there'd be a lot more output capacitors than we have here. But yeah, CPUs aren't as noisy as GPUs are, so you don't need that much capacitance, and the current handling capacity is just like that's mainly a power stage thing. The capacitors don't really play a role in that. So yeah, for a 9950X, massive overkill, and then 500 amps, which yeah, you're not like that. That's just not happening on this socket because the CPUs just don't pull that much current. About 42 watts of heat. So at this point, the heatsinks very much become necessary, but also this isn't happening. Like you're simply not going to put that much power through this CPU socket. So yeah, the VCore VRM on this is massive overkill, which really doesn't surprise me very much because that's kind of the norm for AM5 motherboards. Really makes you question why they even bother putting more and more VRM onto the more expensive boards, because like this is already more than enough. And what I find really funny about this is that this is basically a 4090 VRM. And then like it gets bigger on other higher end boards, which is just like, yep, that's totally necessary. Anyway, so that's the VCore VRM. In terms of current handling capacity, this really shouldn't have any issues powering anything you put in this socket. Actually, you might be able to power two 9950Xs with just one of these boards. So that's fun. Then for the SoC VRM, this is just one power stage per phase, but it is the same power stages because yeah, like it doesn't really make a ton of sense to buy like two different parts for your motherboard when you're already using 14 of one power stage for the rest of it. So the SoC VRM is somewhat, in a way, more overkill than the VCore VRM because the SoC power rail struggles to output any, like, if you're really, really pushing it, it might output 20 amps. I guess if you ran an APU, right, and you were like you were using the iGPU a lot, you'd see more than 20 amps of SoC output current. But with the Ryzen CPUs, like the SoC power rail really doesn't need to provide a lot of current. And so yeah, at 20 amps, that's less than 10, in most circumstances, you're going to be outputting less than 10 amps per power stage. Like, you're not going to even be reaching the, like, peak of the efficiency curve for these. Because the peak of the efficiency curve for these is somewhere between, like, 10 and 20 amps. Yeah, this is so much power stage that, honestly, it might be more efficient if they went with one phase instead of two. Though there are upsides in terms of voltage regulation, potential upsides in terms of like voltage regulation to having two phases instead of just one. But yeah, I do find that kind of funny. That SoC power delivery is just massive overkill. You know what else is massive overkill? VDD MISC. VDD MISC on some motherboards is provided by a single chip that is just an integrated buck like controller, driver, and both high side and low side MOSFET. Not here though. No, here we have this chip for controlling the VDD MISC, which what I find really funny about this thing is this has like more, this is basically the same size as the VCore VRM controller, right? Like physical footprint is basically the same as the VCore VRM controller. But this chip is a Richtech RT 3672EE, which is actually very common for VDD MISC power delivery on AM5 motherboards. But this is like a two-phase controller, and like half of the pins on this package are unused, which I just find kind of interesting that you have such a big chip with so few useful outputs on it. Um, it's not super often that you see something like that, and then at least not on motherboards. I don't know about other elsewhere, but like yeah, on motherboards this is a bit weird to see such a big chip with so few outputs. And here, this like it's literally bigger than the power stage it's controlling, which yeah, it controls one power stage, single phase VDD MISC, and that one power stage is an Alpha and Omega Semiconductor AOZ 5516, and this is a 55 amp DRMOS component. Yeah, VDD MISC outputs even less current than VSOC. So this is massive overkill again. But yeah, that's kind of the norm for AM5 motherboards. So, yeah. Yeah, like, honestly, I suspect that the 40 gigabit per second USB chip probably needs more cooling than well, okay, not more cooling, but the heatsink that it comes with is probably more important for the USB chip than the heatsink that the VRM has. Because, well, the VRM takes up significantly more space, so, you know, it has a easier time dissipating whatever heat it generates. And also the VRM is just massive overkill. So, yeah. Um, so that's that in terms of the current handling capability for the VRM. Now, in terms of capacitor configuration and, well, inductor selection, so let's go with the inductors first. VDD MISC is 100 nanohenries. This is pretty standard for VDD MISC, which I find kind of interesting because 100 nanohenries on a GPU would not look out of place. On a motherboard is surprisingly low inductance. But then the VDD MISC also has like a lot of multi-layer ceramics on the output of it, so I guess there's some like voltage regulation criteria that's easier to achieve with a very low inductance. Because as far as like current handling capacity goes, this really isn't necessary. To have like such a, because the thing with low inductance inductors is it's generally easier to get very high current handling capability and at low inductances. And so, yeah, this is kind of interesting, but also pretty typical. That like 100 nanohenry inductor for VDD MISC. So that's that. Then vCore and VSOC use 200 nanohenries, which is still kind of on the low end for motherboards. 200 nanohenry per inductor, especially in a teamed power stage setup where two power stages switch on and off at the same time. Because effectively, when these two power stages turn on at the same time, the inductance ends up being about it ends up being like 100 nanohenries. So the upsides to this is that for a given size of inductor, lower inductance generally means that you're going to have less DC resistance, so lower power losses in the inductors. Also, the lower inductance can translate to less overshoot on load release transients and just generally better transient response. But the overall transient response also depends on like the capacitor configuration and the tuning of the VRM controller. And I haven't measured the board with the oscilloscope yet, so I don't know how good the transient response is. In terms of the capacitor selection, it's pretty standard. Like it's like very standard. So vCore bulk output filtering here is just these 560 microfarad Nippon Chemicon through-hole polymers rated for 10,000 hours at 105 degrees Celsius. And there's 8 of them. So, yeah. And this is pretty typical for a motherboard. Like this really isn't anything special. What I find kind of funny about this is like there are some AM5 motherboards that just have insane amounts of bulk capacitance, and I am relatively certain it doesn't do anything. Which, like, so basically I agree with MSI's decision to just use 8 560 microfarad through-hole polymers. Yeah. I mean, like the thing with motherboards is a lot of your transient response is just limited by the CPU socket itself. So doing you don't have like on GPUs, it's pretty standard. Like if let's say this was a 4090, I would be expecting to see like twice as many capacitors and more capacitance per capacitor. But this is a motherboard, so yeah, this makes sense. Anyway, the SoC power rail, on the other hand, is actually uh, kind of massive, right? Because so vCore you have 14 phases, and 8 capacitors. SoC you have 2 phases and 4 capacitors. Same spec, still 560 microfarad, 6.3 volts. And I guess the main reason for this is, again, if you're powering an iGPU, you might actually need more bulk capacitance than CPU vCore power delivery does. So, yeah, like there's a lot of capacitance on VSOC. Also, what's kind of interesting is that on VSOC we have some multi-layer ceramics mixed in right around the inductors, whereas on vCore you can see that there are footprints for capacitors that MSI just decided not to populate. I guess they came to the conclusion that they didn't do anything, which seems reasonable to me. As like for CPU power delivery, that really wouldn't surprise me if that was the case. VDD MISC is 2 560s. And this isn't really anything weird. Like, yeah, it's like 1 phase and 2 capacitors, but yeah, that's not too surprising. Probably massive overkill, though. Yeah. VDDIO, which I kind of forgot to talk about. So that's like the main CPU power rails. So MSI, in terms of in terms of current handling capacity, massive overkill. In terms of inductor and capacitor selection, we have rather low inductance inductors, so that could be good for transient response. In terms of capacitor selection, pretty standard stuff. Really nothing special for the bulk capacitance. And then in the CPU socket, it's a bit light on the capacitors. Like, interesting layout, which I'm wondering, I wonder if this is to optimize the ESL or something. Because there are, depending on how you lay out the capacitors, you can get, lower inductance in the PCB itself. Because it's not really typical to see this many, diagonal capacitors in a CPU socket. But at the same time, what I find interesting is that this is really not a lot of capacitance in this CPU socket, right? Like, we have OC, like a lot of other motherboards will have especially Asus likes to just pack the socket with ceramic, and MSI isn't doing that. Right? We just have some 0603s and then some I'm pretty sure those are 0402s mixed in, which is weird to see on a CPU socket. The really really little ones, because CPU sockets usually have entirely too much impedance to benefit from these. At least as far as I know. So I do find that kind of interesting that they've gone with these really little ones for what, here we should have vCore right here. So yeah, bit odd. But I haven't measured it with the oscilloscope yet, so I don't know. Maybe this works really well, or maybe it's just, to be fair, so far most of the AM5 motherboards I've measured, even though they have drastically different approaches to capacitor and inductor selection, and then also the ceramics in the socket, a lot of them end up measuring the same, which I find kind of disappointing. So, because, you'd be hoping that if there's such drastic differences in component selection, it would actually translate into something in the measurements, but it very often doesn't. So, yeah. Whereas, what I find funny about that is on GPUs, it's very noticeable. And I think it's because GPUs are BGA. So I suspect what's happening is basically a lot of what you measure on the back of a GPU is just blocked by the CPU socket on a motherboard. It just doesn't get out of the substrate. And so what you do on the motherboard just matters so much less. Anyway, let's talk about the VDDIO. So controller is this, single phase VDDIO, of course. The controller is this chip over here. It's some kind of Richtech thing, and I didn't bother decoding the part number because it really doesn't matter that much. But and Richtech has the worst part number. markings on their ICs, because they're basically impossible to Google. And the only way to figure out what it actually is to open up the datasheet and then scroll to the marking decode, which is annoying. So yeah, you can't search these, so I didn't bother. But it's a single phase Richtech controller, which is pretty standard for, well, like this is basically the power delivery for the memory on a DDR4 motherboard. So yeah, this really hasn't changed. It actually just has to do less work than it used to, right? On a DDR4 motherboard, this would also power the memory sticks, while on DDR5, it only powers the CPU's memory controller. Well, not even the memory controller, just the PHY. And in terms of MOSFETs, we've got more alpha and omega semiconductor parts, one high side, one low side. This also integrates the driver circuitry. So this is like controller and driver combined. And the MOSFETs used are AONS 36303s. And I didn't bother to write down what their RDS on is, which was really stupid of me. But like, this is more than enough for VDDIO. Like this basically is a DDR4 VRM, except now it only has to power the PHY. Also, we have this adorable little input filtering inductor over here. So, yeah. 220 nanohenries for the inductor for VDDIO, which is kind of low for VDDIO, I think, compared to some other boards. And then we have a kind of a lot of output capacitance, right? 3 560 microfarad capacitors. This one over here is input. So, and you might be wondering, wait, what? How's that input? So, because this is like a 6.3 volt capacitor, how can it be input? So, VCore, VSOC, VDD, MISC, those all run off of 12 volts, right? Like that's 12 volts coming in. But VDDIO is getting 5 volts from the 24 pin, right? So that's 5 volts, goes through this little inductor here, and then this is the filtering for that. So yeah, this is a input filtering capacitor over here. Then for the memory, well, we have another input filtering capacitor over here that's like more for the memory sticks. All right, because the memory sticks get 5 volts coming into them through the top couple pins of the memory slots. And since we're already on the topic of input filtering, the VCore VRM and like VSOC input filtering and VDD MISC as well, like they're all sharing this capacitor bank. What I find kind of funny is how we have this 100 microfarad just hanging out over here. I guess MSI came to the conclusion that VSOC needs some extra input filtering or something. Because yeah, all the rest of the input filtering is over here. And these are 270 microfarads, 16 volts, Nippon Chemicons again, 10,000 hours at 105 degrees Celsius through hole polymers. Pretty, like, another very standard input filtering capacitor configuration. And then, of course, we just have multi-layer ceramics directly behind the power stages, right, for dealing with the turn-on, turn-off transients. Well, mainly the turn-on transient of the high-side MOSFET. So, yeah. So, as far as like capacitor selection and just power delivery in general, I really don't have any complaints here. Right. So let's move on to the memory. So I already mentioned that like the memory just gets 5 volts. Well, it's not straight from the 24 pin. I do think it goes through this MOSFET right here, which gets like potentially turned off. What's kind of interesting is some motherboards will actually have a dedicated like 12 volt to 5 volt regulator for memory power. And then like Asus, MSI, they just take 5 volts straight from the 24 pin, shove it into the memory sticks. I'm not sure that there's any benefits to having a 12 volt to 5 volt converter first. Anyway, as far as the memory topology is concerned, this is your standard daisy chain. So, you know, like that. And it is, like, you could say shielded, because, yeah, we don't see any of the data lines or the command address bus for that matter. which, yeah, like you just don't see anything. On the back of the board, we just have this great big ground fill over everything. Also, you can see here the VDDIO power plane is absolutely enormous. So I find kind of interesting that, like, yeah, it gets so wide, considering that this is where the inductor is connected. You can tell from the stitching. And also you can see how, like, input filtering, output filtering capacitors. Yeah, we have some extra multi-layer ceramics as we get closer to the CPU, because obviously the closer you get to the CPU, the more high frequency, like, noise from the CPU you want to filter out. But yeah, as far as the actual memory topology goes, we can't see any of it. So that's a bit interesting, because there's a lot of AM5 motherboards where you'll see, like, the command address bus on the back of the board. But yeah, MSI put everything inside. I don't know if there's necessarily any upsides or downsides to that. And on the top layer, we have what looks like a giant ground fill as well. Also, because this is a daisy chain, you should use this memory slot and this memory slot first. Well, I've messed around a little bit with memory overclocking on this board. I mean, the issue is my 9950X kind of sucks for 2-to-1 mode. Though I was surprised at how stable it was, because my 9950X, especially a DDR5 8000, on other boards is just completely unusable. On this board, it ran for a bit before it inevitably crashed anyway, but yeah, I was honestly kind of surprised that it wasn't just immediately crashing. Though I think that might be more of a BIOS tuning thing than necessarily a topology thing. Because when I tested this board with 7000 series, it was really not great. Like, I have a 7950X that is quite capable of doing DDR5 8000 on some boards. On this board, it, like, even 7800 was a struggle. So as far as I can tell, MSI seems to have put most of their effort with tuning the BIOS on this board for 9000 series, and 7000 series they haven't really bothered, which makes sense. It's an X870 board, so don't really, like, I'm not going to complain about that. So yeah, that's the X870 Tomahawk Wi-Fi. And in terms of components, I like it. I mean, there's not, like, they're not doing anything super special. But at this price point, like, I just want a postcode. And I got that. The VRM is going to power any CPU that you can put into the socket. Voltage regulation, I do still need to measure that. Memory overclocking, that's going to need more testing. In 1-to-1 mode, it works great, but 1-to-1 mode, in my opinion, isn't really much of a motherboard test. So, yeah, I wouldn't, like, getting good results in 1-to-1 mode is, like, not really... I don't really consider that indicative of the motherboard's capabilities. So... yeah, that's the X870 Tomahawk. So big thank you to MSI for sending over a board for testing. And thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, there are links in the description that you could check out, and that would be much appreciated. And yeah, that's it for the video. So thank you for watching, and goodbye.